Welcome to this presentation of our work on uncertainty quantification in medical image segmentation using normalizing flows. My name is Raghav. So medical image segmentation is an inherently ambiguous task. For instance, here we see an input image, a CT scan, and then four different expert human annotators who see very different things. So capturing this uncertainty due to these factors can be very useful in downstream clinical tasks. And then how do we do this in a meaningful way is sort of the larger objective of this work. So CNN-based segmentation models have become the state of the art, but bulk of these methods do what I call, or the literature calls as point estimates, meaning for each input image, you get a single estimate. Another principled approach is based on generative models such as the VAEs seen here in a conditional setup. And then the most popular one has been the probabilistic unit, which basically uses a conditional VAE sort of formulation to obtain a latent posterior distribution from which several candidate segmentations can be obtained. Now, both these models rely on the CVAE assumption of using the latent posterior distribution or the encoded distribution from of the VAE by mapping it to normal distribution. Now, can we do better than Gaussian latent posterior distributions so that we can capture richer diversities in the segmentation? Now, that's the question we answer in this work. So in terms of background, the key idea used in this work is the normalizing flows. Now, in essence, normalizing flows are standard transformations of probability densities and distributions from simple to complex ones using sequential maps. Now, for instance, if we have a base distribution, which is Gaussian in this case, then we want to transform it to a target distribution, which is a mixture model here with 4 modes. Now, how is that done? So now normalizing flows basically comprise of what are called bijective transformations, so reversible maps. And then we can compose complex transformations using simpler ones, seen here as T, composed of K individual bijectives. Now, this transformation is applied recursively, starting with a base distribution Z0, which perhaps is distributed from a simple to sample from distribution like a uniform or a standard Gaussian. Now, once you have a random variable and then you transform it with a map such as T here, the transform density is adjusted by the change in volume of this transformation, which is captured here using the Jacobian determinant. And this is like a standard result. Normalizing flows basically expand on this notion of taking a random variable and then warping that space, in sequence. Now, once we have like a chain of this, so the full transformation is basically here in the log domain, seen as the input density adjusted by the sum of the log Jacobian determinant. Here's a quick visualization of the previous case where we wanted to transform our base distribution to a standard one to show what happens. And then we use the affine or the planar flows. So now at the first, and then here we use 10 steps of a flow chain. So this is at input, where the green space, green grid is basically the space of the input distribution. And then we see after each flow step, what happens in here. As we see that the Jacobian determinant is basically determining the amount of squeeze at each point in this space. Now, as we progress through the normalizing flow chain, we see that the space is getting warped, so that it can map closer to the target distribution. So now at the end of, in this case, this is using 10 steps. And then we see that our input-based distribution now is mapped into this space. So in our proposed method, what we do is in a probabilistic unit or a hierarchical segmentation model. So we have a single random variable or a hierarchical random variable in the latter case. So what we basically do is assume something like a CVAE model, as in the probabilistic unit, and then instead of remaining in the latent posterior distribution, which is Gaussian, we use a sequence of normalizing flow steps here, using which we start from like a standard Gaussian, not a standard Gaussian, but then a Gaussian encoded distribution, and then transform it into K steps so that we end up capturing a richer posterior distribution from which we can sample more diverse segmentations, hopefully. Now, putting these together, we obtain our model conditional flow net, which is basically a CVAE type model with normalizing flow. So now here, let's look at what the training process would be. So pairs of input and segmentations are given to the encoder neural net, which predicts the mean and the standard deviation of the base random variable in the encoder Z0, which is then transformed using K steps of flow. And it also obtains a context here, which is based on X and S, so which feeds additional information to each of the random variable here. And once we have taken Z0 and then transformed it into our target distribution, which perhaps hopefully is richer, then we regularize that with a prior distribution, and then the standard CVAE type of framework goes on here. We can sample from this latent distribution, which now hopefully has captured richer variations, and then we decode that to obtain our segmentations. Now, what type of flow we use in this work, just to demonstrate that it can be, we use one of the earlier flows, that was the planar or the affine flows from this work, and then one of the more successful recent one, the generative flows, the GLOW model. So, and then both show, as we will see, very comparable performance. So what are the experiments? So we perform experiments on two data sets. One is the LIDC data set for lung lesion segmentation, and then here we have 4 expert raters to train from. And then we also use the retinal vessel segmentation data set. And we compare the performance of the model using the generalized energy distance. Now, how do we perform here? So for the LIDC data set, when our model is trained on all the raters, we see that the planar flow, so this distance, lower the distance, it captures better or richer diversity. So we have a lower measure here. And then the probabilistic unit basically is our baseline here. And then we are able to perform quite well in this regard. And another very interesting thing is with our model, when we train using not all 4 raters on the LIDC dataset, just a single rater, we are still able to kind of, in terms of the generalized energy distance, we are able to outperform the probabilistic unit very well. So meaning we can learn diverse segmentations just when trained using a single rater. And this holds even for the retinal dataset. So here's some qualitative examples of one case. In this row, we see the predicted, this is a test set example. So when the input image is this one, so we have showing like 8 different candidate segmentations obtained from the proposed model when trained with all the raters. And then here, when trained with a single rater, and then the same sort of a behavior when for the probabilistic unit. And then we see that not only the segmentations are sharper, but then the diversity captures the ground truth segmentations. So now, in conclusion, normalizing flows can be used to obtain diverse segmentations. We only use a single latent variable that is transformed sequentially using K steps of flow. As we've seen, the performance is quite comparable with the other methods, and then we show a big improvement even in some of the tasks. While we've demonstrated this with using the GLOW and then the planar flow, so any sort of reasonably complex flow block can be used here. So now, because we introduced the flow block here, so there are additional hyperparameters that need to be tuned, which are specific to the normalizing flow model. Unlike in exact likelihood optimization that can be done using flow models, here, because we integrated with a conditional VAE, we are still optimizing a form of elbow. So if you have any questions, shoot a mail or stop by the poster session, and the model and the code will be available at this link soon.